Hello, everyone, and thank you for joining us. Welcome to today's webinar. It's episode 32 of our Graph Gurus series, or sorry, episode 33, I should say. They're coming thick and fast. I can barely keep up with the number. It's hard to believe we've done 33 of these webinars already. Today's is an especially interesting one. It's part 2 in a series on GSQL writing best practices. I don't know yet how many parts there'll be altogether, but I'm fairly confident there'll be a part 3, and I don't know beyond that. Today's episode has a very intriguing title, A Better Plan, and we'll find out shortly what that involves. My name is David Ronald. I'm Director of Product Marketing at Tigergraph. My degrees are mostly in physics, and I worked in artificial intelligence, NLP, telecommunications, and data analytics. But much more importantly, this is today's presenter, my esteemed colleague, Xingyu Chang. Xingyu has been with Tigergraph for 5 years and 7 months, I think, if memory serves. He joined the company as a solutions architect and software engineer back in July of 2014, and has been moving up the company in terms of his seniority as a direct consequence of him demonstrating his expertise and his capabilities. And he is now our Director of Customer Solutions with a team of 4 or even 5 people, perhaps more, working for him. He has a very interesting background. He has a master's degree from Kent State in computer science. He's working on a PhD also in computer science, and also intriguingly, his bachelor's degree was from Dalian University in China, and he studied computer science and Japanese, which I think is a testimony to his not only his intellect but also his curiosity. I think most appropriately for today's webinar, Xingyu co-authored GSQL, which is the query language that we use with our graph, and which is helping to influence the GQL standard that the ISO body is currently working towards. So Xingyu is highly qualified to give this webinar today on query writing best practices. Before we get started, a few housekeeping items. As always, your phones are muted. Please submit questions through the Q&A tab. We do want this webinar to be as productive for you as possible. So the more questions you submit, the more you can influence the way it evolves. So please don't be shy. Submit your questions at any time, and we'll do our very best to get them all answered before we wrap up. The webinar is being recorded and will be uploaded to our website. We're very quick about doing this. Usually it's done within 2 or 3 hours, so later today. And additionally, we'll send out an email with a link to the archive webinar, the slides, and any other materials that Xingyu thinks are helpful and should be included in that email. Last but not least, it's very rare these days, well, don't know, with all the demand on Zoom, but certainly Zoom does seem to be much more stable than it was when we first started this series. If, however, you do have any questions or any issues with Zoom, please reach out to us and we'll do our best to handle them. And with that, I am going to stop sharing and pass control of the webinar to Xingyu.
Okay, thank you, David, for this great introduction. So let me share my screen. Okay, so in previous episode, I talked about like the things to think about when we write a query, right? Such as like, where do we start from? What is the traversal plan? What edges should we use? And what accumulators should we use to answer a question like with a GSQL query, right? And so this time, we will add more to that. Is that it's about like when we design a traversal plan, because the answer is not unique, right? We can have multiple different answers, different ways to traverse the graph to get the same result. So today we'll learn about what to think about to find out what is the best plan, right? So what is the traversal plan that is the most efficient and the most memory saving? Okay, so this is the today's agenda. We will review more basics, okay, and then I'll explain, give you a few examples on what is a better traversal plan and what are the choices. And then I'll show you how to check the log, because checking the log is very essential, because we need a lot of information to design a better traversal plan, right? So basically the informations are the number of vertices and the edges in your graph, as well as how many has been traversed in your current query, right? We need to tune the query while looking at the logs. And then I will give you 2 examples, okay? So let's review some basics first. And this is almost the most frequently asked question. The question is, what is accum and post-accum, right? So this is almost the most fundamental part of the GSQL query language, is the accum and the post-accum clause. So easily speaking, post-accum and post-accum, they do map and reduce, right? So this is a simple chart showing you what the process of map and reduce. If you are already very familiar with Hadoop, then this is not very hard for you. If you don't have much like a map reduce experience, I will just explain this really quick. Okay, so map reduce, like it's obvious, like by its name, it has 2 phases: map phase and the reduce phase. So the map phase executes in parallel. Each map does the same job, and then after the parallel computation, it will produce a result, and the result is reduced based on certain rules, and reduce the 2. We also run a reduce job in parallel to aggregate the result into final. Okay, so this is the 2-phase map reduce. And the post-accum and the accum clauses, they are running things that they're running in a way is extremely similar to map reduce. Okay, so so here are some essentials of accum and post-accum. So accum runs on the edges, right? And the post-accum runs on the vertices after accum. Okay, so in our training, actually, I would repeat this part again and again and again, because well, I really want the audience to remember this, right? So this is I always repeat. Okay, accum runs on the edges, post on the vertices, so that we know what to do when we write a query. Okay, and another thing is both accum and the post-accum are running logic of map. Why is map logic? Because both accum and the post-accum, they run in parallel, right? Because accum run on the edges and all the edges run the same job in parallel, just like a map does. And it will produce a result, right? And so is the post-accum run on the vertices in parallel and also produce a result. And in the after accum and the post-accum, there is a hidden phase. Reduce phase is executed to aggregate the result produced by accum and post-accum. Okay, so here are some examples. For example, if we have a social graph, 2 users become friend at a certain timestamp at a certain date, right? And a user can have age and gender. And in this case, this is the example, very good example of accum clause. Okay, so now we ask question: what is age distribution of friends that were registered in 2018? Right? So we have a query like this. We have a map. We have an integer as a key, and the integer is the age bucket. Every 10 years is a bucket. Okay, and the value is the number of users falls into that bucket, become friends, right, in 2018. So now we have this query. We will use this where clause to filter out all the other users that to filter out the user is not like like become friends not in 2018. And then we populate the map in the accum clause. See, if we look at this accum clause, it happens on all the edges selected. So these are the edges. These 4 edges are the edges being selected. So the first thing is execute is where clause. So where clause happens on all the edges, right? And it filters out the edge having the attribute. For example, this date. The connect date is 2019, so this one is filtered out. And then now we leave only these three edges will execute the logic defined in the accum clause. And this logic will be executed in parallel on these 3 edges. Okay, and then after where clause, we execute the accum clause. And in the accum clause, it will do a map logic, right? It runs in parallel, it does the same thing, and send the result like this to the map. So age divided by 10, that's the age bucket, and 1 is the number of user, right? Because each edge is 1 user. And then, like first edge, the age of the user is 25, divided by 10 is 2, right? It will send 2, 1. 2 as key, 1 as value. And second edge, the age of user is 28, and then the age divided by 10 is also 2, and the user count is 1. And for the third edge, the age is 31, and then the age bucket is 3, and the user count is 1. And these are the result being result of the map phase. And then these are sent to the global accumulator, which is stored outside the graph in the global memory, right? And then these messages are sent to the map, and then there is a hidden reduce phase or aggregate phase to aggregate these keys into the map. So we have two, like a two key, like a value 2, right? So they will be aggregated into the same key value. So after aggregating all the messages or the values, then this is the final value of this age map. And this is the distribution of the ages, right? There are 2 friends in their 20s and 1 friend in their 30s. Okay, so that's the accum clause. From accum clause, we can assign value to a global accumulator. And also from accum clause, we can also assign value to a local accumulator. So here you can see, because we need to design this type of accumulator, because we are assigning value to this map from multiple edges to 1 variable, right? So that we need to follow the map reduce structure, that we send the messages from multiple places and aggregate them afterward. Right, and then this is an example that how we assign value to local accumulators. So now this query outputs the average age of common friend. Like for example, the common friend between input user and user E is user A, B, and C, right? And now we want to figure out for each second half friend, what is the average age of the common friend, okay? So now if we look at the query, we define the local accumulator called average accum. And then in this line, we populate the value of the average accum from accum, right? So first thing, we want to select the first half friend, and this is how we do it, right? We have talked enough about what is select statement last time. And then starting from 1 half friend, we traverse to second half friend. And then during the traversal, for all the edges in the second half, we run this logic, right? That is to send the age of the common friend to the accumulator stored on the second half friend. So T is the alias of the second half friend. So in this case, user E, F, and G, they are T in this query, right? And this average age variable accumulator belongs to T, right? So they are these variables or local accumulators. And now we are sending the age number of s dot h. So s here is the second hop neighbor, right? You can see it's an alias. Oh, sorry, I got it wrong. So s is the alias of the first hop neighbor. You can see it's defined right here, referring to the first hop friend. And now I'm sending the age of first hop friend to the average age local accumulator on the second hop. Okay, so that's what has happened. Okay, so this logic execute on every each edge, right? It will send the ages to the average accum, right? So that's what happened during the accum phase. And then after accum phase, there is a hidden aggregate phase, right? We will aggregate all these value into the local accumulator so that on the second hop friends, they get the average age of the common friend in the first hop. Okay, so this is just to follow the pattern of map and reduce. Accum is map and the aggregate is reduce. And then post-accum, same thing, because post-accum happens on all the vertices and they also run in parallel to execute the logic defined in post-accum. Okay, so what this query does is it will calculate a normalized number of common friend for each person in the set. Okay, so that is, so again, like for input use between input user and user E, the common friend is ABC, right? So this guy will have common friend 3, user F will have common friend number 2, and user G will have common friend number 1, right? So in this case, we'll run select first, and then we will run a accum. That is a accum in the in line number 9, right? We calculate the common friend because we have an accumulator called a CNUM is the common friend number, and then we do it in line and number 9, right? We send 1 to the local accumulator stored on the second hop friend. Like we send 1 to the CNUM stored on T, and the T here is the second hop friend, right? And then after that, we aggregate, we get the total common friend number 3, 2, and 1, right? And then we execute the logic in line number 10. We want to find the global maximum in order to calculate the normalized value, right? So from each vertex, so this is the post-accum, right? Post-accum execute on the vertices. And from each vertex, I send the value CNUM to the global variable max CNUM. That is the global maximum common friend number. Okay, so we will send the value 1, 2, 3 from here, here, and here to the global variable. And after that, there is the aggregate phase. We get the final value of the global accumulator 3. Okay, and after that, we want to calculate the normalized value. That is the common friend number divided by the global maximum, right? That's the easiest way to calculate the normalized value. And then again, from post-accum, runs on every each vertex, we divide this CNUM value by the global maximum 3 for every each vertex, and then get the final value of the normalized friend number. Okay, so this is the introduction of what is accum and what is post-accum. And now let's go to the topic, like how to design a better traversal plan, right? So these are the few things we can think about. Like first, we can design we want to always choose the lightest weight traversal path, right? We want to find out what is the path that can traverse the minimum number of vertex and edges, right? And sometimes when we start somewhere, like when we run the query, we want to start from somewhere, right? We need to think twice before we start from a type or all the vertices. And sometimes we can consider to make our algorithm bidirectional. And also we need to think about how to avoid the hub nodes. And sometimes we need to traverse back a little bit, like moonwalk, right? And also what to do when we search for multiple search conditions. Okay, so now assume we already have a enterprise graph. This is like a Crunchbase, right? in Crunchbase, we know like which country a company domiciles the domicile in, right? And also we know like one company is the parent company of another company. Okay, so now so it's very similar to relational database query optimization. So it always starts from a smaller set, right? So now if we ask a question to this enterprise graph, so say, find the US domiciled companies that have ultimate parent company in country Z. And the Z is a smaller country, has fewer companies than US, right? What is the best traversal plan? What are the choices, right? So, okay, let's see what are the options. So option one, we can directly start from US, right? Start from US, find all the US companies, and then we traverse all the way up to the ultimate parent, say, oh, are you in country Z or not, right? So this way, the query will traverse very huge amount of vertex and edges, because in US alone, it may have 14 million US companies, right? And the total number of edges traversed is in like hundreds of millions level. However, if we traverse the other way around, we start from country Z. Country Z may only have 20K companies. And in that way, we traverse all the way to its subsidiaries and see if they are in US. It's a lot more lightweighted, and the total number of edges traversed is way below like 1 million. So that you can see the different starting point is so important that it may impact the scale of the query like 100 times, right? It's really like the difference is like a day and night. And also another thing is sometimes we need to think about where should we start from, right? We need to always think about, like, before writing the query, we need to think about where does this query start from? And this is a very common mistake made by like a GSQL query beginner writers, right? They would like, because it's very similar to relational database, relational would do this, right? Select star from something where what equal some columns equals to a value, right? But in GSQL, if we write it this way, if we want to find the company and say we start from all the companies and check S is the alias of company, right? And it is also the ID of the vertex. S equals to V, V is the input of vertex. So by doing this, we actually go over all the companies there is in the graph database and to check whose ID equals to the input. So this is very expensive. If you have 100 million companies in your graph database, then you scan over all the 100 million vertices to check whose ID is your input, right? So the recommended way is always like we take company vertex input and we create a vertex set out of it. So this way, it almost takes nothing. It's constant time to find a vertex in the graph database. And then you can create a vertex set out of it and you can start traversal from it. So when we write a query, when we write something like this, we start from a type, we start from all the vertices. We really need to think about this. We need to think twice. Do we really have to start from everything, or can we start from only a small set of IDs? Yeah. So, or are we running something like a PageRank that it needs to involve everyone? If it is the case, it's the right thing to do. Okay. And also sometimes we can consider to traverse the graph bidirectionally. So for example, of like a shortest path. Okay. So given the source and the target, if we only start from the source, and when we reach, we traverse the graph single directionally when we reach the target. So this will be the graph we touch up by when we find the target. Okay, so you traverse 1, 2, 3, 4 hops. These are the, you may touch this many vertices when you find target. Okay, So if we traverse bidirectionally, we start from both source and the target and have the passes meet in the middle. We only traverse this much of vertices and edges. You can see it's a lot fewer than traverse single directionally. So when we do shortest path like a query or circle detection like a query, we can consider to traverse in both directions. So this will significantly reduce the number of vertices and the edges traversed. And another thing is hub node or supernodes in your graph. So hub node and supernodes are the vertices has very huge amount of neighbors. It can have millions of neighbors or 100 millions of neighbors. So when your traversal, when your query like traverse this vertex and you need to start from them, you touch a very large portion of the graph and it really hinders your query. Okay, so so there are a few ways to avoid starting from the hub nodes, and that is also very important thing to consider when we design a better traversal plan. Okay, so for example, given company A, find and oh, sorry, am I off? Am I cut off?
I can hear you, Xingyu.
Okay, good, good. So in this case, E and H were selected because they share the same CEO and the country. But however, you can see this many vertex edges were traversed because US can be a hub node having like a 14 million companies in US, right? And alternatively, if we optimize this plan a little bit, say we start from A and we traverse to the CEO first, and then also find other companies being run by Jill, right? And then we check which companies are among those companies, like H, B, and or like a domiciled in US, right? And you can see this way, we traverse way less edges than the previous traversal plan. Okay, so similarly, if we sometimes we ask a question, okay? So given company one, we want to find the company two that are shares this list of attribute 1, 2, and 3, right? So in this case, if we want to design the optimal traversal plan, one thing we can look at is the number of vertices and edges, right? So in this case, if attribute 1 only have 10 vertices in the graph, and the attribute 2 has 1 million, attribute 3 has 100K, right? And the edge number is pretty much the same, 100 million for each, right? So in this case, we always want to consider, we can consider that, can we start from attribute 2 alone first? Because attribute 2 is very special to each company, right? So we can filter out most of the company by traverse attribute 2 first, and then come back, see, okay, if you get the right attribute 1 or 3. Otherwise, if we go attribute 1 directly or all of them together, then hopefully you will, like the average out degree of attribute 1 is about 10 million, right? So hopefully we will like end up traverse a lot of vertex and edges. So in this case, we always want to start with the attribute, the common attribute that is the most special. Okay, and another way of dealing with hub node is that we can filter them out, because sometimes for like a or anti-fraud or analytic that doesn't require you to have a very accurate result. Like a approximated result is good enough. Then this way you can just consider to filter out those hub node by using a where clause or a sample clause to like a sample 100 edges from those hub node. Okay, and another way is we can also split the hub node at the schema level. For example, we have a hub node that has millions and millions of vertices, and then we can build the index to them. Say we can split, say the transactions or actions to days, right? Because we only have 300 days a year. 10 years, it was only 3,000 days. In this case, the hub node is no longer a hub node if we only select a certain period of time, right? Okay, so this is ideas how we design a better traversal plan so that we traverse less vertex and edges so that your query can be a lot faster. Okay, but to design a better traversal plan, that requires the knowledge, right? So where does the knowledge come from? Of course, one thing is we know the number of vertex and edges in the graph, right? That's one thing. Another thing is it is from the log. Sometimes when you run the query, you find it, oh, it might be slow. So first thing we want to do is we can take a look at the log, see what is the most of time spent like for a given query, which select statement spend the most of the time. By looking at the log, you can tell you right? And then later you can think about, okay, what to do to optimize this query. So this is also like the daily work as a solution architect. Sometimes customer says, oh, can you further improve this query? Well, yeah, let's take a look at the log first, right? So that's the very essential skill of a query writer. So to understand the log, we need to touch a little bit of touch a little bit of the system architecture, like how the query execute, right? So first thing, when the user send a query, the first stop is Nginx. Nginx is our web server, and the web server forward this query to the REST-PP service. So this REST-PP service is the you can think it's the load balancer, right? It will do two things. It will send the request to GSE to translate the external ID to internal ID. And then the translated result will be sent to GPE, and the GPE will do all the MPP, massive parallel processing. And after the calculation, it will send the result for GSE to translation from internal ID to external ID, and also the response is on REST-BP, and REST-BP will forward the result to Nginx, and the Nginx send it back to the user. So that's the execution flow of the query, okay? And every step in this flow chart, you can find some corresponding logs from our log files, okay? So if you run gdmin log command, you can list all the logs, okay? Are you, David, are you able to see my command line?
Yeah.
Okay, good. So.
Oh no, sorry. The command line, no, we cannot see.
Okay, let me share my entire screen.
Yep.
Okay. How about now?
Yeah, yep, perfect.
Okay, good. So by running this simple, you cannot see it?
That's good. We can see it.
Oh, good. It's my like a visual machine, right?
Yeah.
Okay, good. So by running this gdmin log command, you can list all the logs, not all the logs, most useful logs of a telegraph system. Okay, so and this, and now I'm talking sorry about that. I'll talk about how to check the logs from the Nginx, because Nginx is the first stop, right? So when the query was run, this is the first line of log you can see that is from the Nginx server log, right? And then after it forward the request to REST-PP, you can see a new line is printed with the request ID, okay? And for the rest of the log, it's always this request ID. By using this request ID, you can find them from GSE log, GPE log, see how it executes. Okay, so this is almost the most important log to look at. That is the GPE log. So by grabbing the request ID, you can find all the execution plan of this query. And here, you can see this is when the query is gets started, and this is a query running the select statement. So here, iteration 1, 2, and 3, they are different select statements. Okay, so and for each select statement, we know that it has like a accum clause and a post accum clause, right? So here, edge maps means accum clause, okay? Because accum clause executes on the edges, right? So if it says 2 edge maps, that means there are 2 edges executed the logic defined in accum clause, okay? And here it shows how long it took to execute those two, to run the logics from those two, to traverse those 2 edges, right? And here it says 2 vertex reduces. So I think it's easy to guess. This is for your post accum, right? Because post accum runs on the vertices. And here, that means 2 edges, 2 vertices has was executed, performed the logic defined the post accum. And this is how long it took, how long it had, the time has been spent in your post accum, right? And here, activated 2 vertices. That means there were 2 vertices being selected and stored in the new vertex set variable. Okay, and here, by looking at this keyword UDF, and you can see the overall execution time in GPE. Okay, so that means this query totally took 0.7 milliseconds. And here is the response size being sent to REST PV server. Okay, so when we want to do tuning of the query, so this is the most important log to look at, right? So that we can see the performance of each select, how many vertex and edges being traversed, and how much time has been spent in your accum and post accum, so that we know what's the part taking the most of time, and we know what might be a good action to take in order to optimize your query. Okay, and this is the GSE log, right? So this is the when you receive the request for ID translation from external ID to internal ID, and these 2 lines are the request for translate the internal ID in the result to external ID. Okay, and this is REST BP. So once it receives the result from GPE, it will return the result to Nginx, right? And this is after Nginx is done, it will print something like this in logs. So at this point, the query execution is officially finished, right? And we want to look at this part for performance tuning. And now I will give you some very like live query writing examples to show you like the performance difference of different traversal plans, and as well as I will show you how to look at the log and understand them so that we know what's the performance difference. Okay, so let's review the content of our last episode, right? So we always need to ask a series of questions before we start to write the query, right? So what are the questions? They are like where do you want to start from, right? What are the steps? What are the traversal steps? What are the edges we need to use? And what do we need to be in the result? And what is the info needed? Like what info do we need to collect in order to calculate the result? And and then we can figure out, okay, what accumulator to use? And then how do we gather the information by using the accumulator? And then we print the result. So these are the things to think about when we write a query. So today, again, we will do the same thing again. We will ask these set of questions when we before we start writing the queries, right? And after getting them answered, we will discuss about like between different traversal plans, which one is the best, right? Okay, let's start. So example one, I already talked about this in the previous slides. That is find the US domiciled companies that has ultimate parent company in country Z. Z has fewer companies than the US. Okay, so again, let's go over these questions. Okay, so where do we start from? Okay, so we want to find US domiciled companies that has ultimate company in country Z, right? So it seems we have two options. We can either start from US, right? Or we can start from that country Z. So we have two options this time. And what are the steps? So if we start from US, we need to find all the companies in US, right? And then we find all the ultimate companies by traverse along some invest and acquire edges. And then we traverse all the way to Z. And then we know, okay, these companies are having ultimate parent in Z. Or on the other hand, we can traverse the other way around. We can start from country Z and then find all the ultimate ultimate parent company domiciled in Z, and then find all the subsidiaries and check if they are in the US. So we actually have two options here. And what edges should we use? Of course, we will use domiciled so that we know a company is in one country, right? And for the parent relationship, we want to use invest and acquire edges. And also, again, we will use domiciled. And another thing is here, this schema is from one of the starter kit, that is the Crunchbase starter kit. So in Crunchbase starter kit, we have schemas like this. Okay, so this is the schema of the Crunchbase starter kit. So we have company, and we also have person, and the person can work for a company, and the company is domiciled in the country, and the amount between companies, there are two types of relationship. One is acquire, and the other is invest. So we will use acquire and invest to identify the relationship between the parent company and its subsidiaries. Okay, and what do we want for the final result? We want the list of company, of course. And what is the info needed for the final result, right? So we need to find out like which vertex is the ultimate parent company. We need to find out which company is domiciled in US, which company is domiciled in Z, and the company invest or acquire another company. So we need a lot of info to calculate the final result. And then what accumulator do we have to use? I think this time we will use a list accum to store the final result, right? So, and another trick of writing a query is draw a picture, right? You draw the traversal plan, like the graph you want to traversal. This is a very useful way. Once you can draw it, it's not hard for you to write the query anymore, right? So like let's try to draw something for this case, okay? So now we have like a vertex. So this is our US vertex. And of course, we have a lot of companies in US, right? So these are the companies in US. And each of the company have their parent company, right? So mark, this guy is a company, and this guy is a parent company, right? And the parent company also has another parent company, and each company can have its country, right? So let's say this is a Z, right? Country Z. So this is a pattern we are looking for, right? For US company, so let's say this is a company A, then it has its ultimate parent domiciled in Z. So this guy will be in the result, right? So this is a pattern in the graph we are looking for. So now let's consider how do we write a query, right? If we start from Z, and we can easily find all the companies domiciled in Z that is ultimate company. How do we figure that out? Because it doesn't have any outgoing edge that is being acquired or invested in other companies, right? Then we know that it's an ultimate parent company. If we start from Z, we can traverse all the way down by following the reverse edge. As long as we can find any company is domiciled in US, then it will be in the result. Very simple, right? However, if we want to start from US, in this case, we start from here, then we need to traverse all the way up. And like for all these guys are US companies, right? We need to traverse all the way up until we find a company and its ultimate parent company, and it is in Z. However, there is a problem here. Because when we, in the beginning of traversal, like for company A, we have no idea its parent company is in country Z or not, right? But when we find its ultimate company in country Z, they are very far away, right? We have to know, okay, this is actually has to be the ultimate company of A, but not B, right? Or C, right? So we need to figure out the relationship between this ultimate company and A. That means we have to pass the vertex ID of A all the way to its parent company so that we know at this point, okay, A and Z, this ultimate company is in Z and it has subsidiaries in US that of company A, right? So we need to pass along this company ID all the way up in order to get the result. Okay, now let's start to write the query and look at the logs. Okay, now let's go to my Graph Studio. Okay, now let's start with writing the query starting from company Z. Okay, it should be very easy. From let's say example 1, option 1. So to start from country Z, we want to take a Z as a input, right? It can be any country. It's an input parameter, right? And then we create a vertex set out of it, right? We create a vertex set variable named start out of this input parameter. And then I can find all the companies in the country, right? Okay, so these are the companies in company Z. And then next, if we look at our questions, so we know we start from Z, and then we traverse to the company. And the next thing is we want to find the subsidiaries of this company, Z company, right? Then we need to follow these two edges. But there are undeterministic hops. So we need to use a while loop to implement this logic, right? So let's do a while loop. Say while company size larger than 0, then we just continue to do this, right? So we want to repeat this process, say in order to find the subsidiaries and the subsidiaries of the subsidiaries. So we start from the same vertex and say traverse invest and acquire. What's the correct name? Invest. Okay, so these are the companies being required, right? Well, equals select T from this, the input. So actually input do. Do done. Yes, it's done here. What now? Great. Let's see. While do end. Right. My bad. It's end. Right. Okay. So this is the subsidiaries, right? And now we want to check them if they are in US or not, so that we can put them into the result set, because we know we have decided that we want to use a list accum to store the result, right? So now let's define it. List accum vertex accum, right? Okay, and now we want to say if, okay, we do it in the post accum, right? Post accum happens on all the vertices. Say if the new subsidiary, the country is USA, then if it's USA, then we want to populate the list with a subsidiary vertex, right? So in the end, we can print things out. Okay, this is simple like this, right? But we need to add a little extra so that it doesn't go into loop, because sometimes investment relationship can follow the loop, right? So we want to avoid the loop. So the way of avoid the loop is to define something like this. We don't traverse the vertex again, right? So we want to mark the companies being traversed as visited equals to true. So that, and we also add a where clause. Add a where clause, say, for the new company we traverse, we have to make sure they are false, right? And then whenever we traverse something in the post accum, we say, okay, your visited is true. So that visited, right, there we go. So that's the query. I think it's pretty obvious. Like we start from the country Z, get all its companies, and then traverse all the way down along the path of invest and acquire, right? And whenever a country, whenever a subsidiary is in US, then we put it into the result and then print them out. Okay, now let's compile it and run it. So after running it,
this might answer your question. Electronic component includes terminal.
Okay, thank you, Alexa. So,
anytime. Enjoy your morning, Xinyu.
Okay. So after running the query, I'll show you how to check the logs so that we can see the performance difference between a good traversal plan and a non-optimal one. Okay. Okay, done. So now let's run it. Let's start from any country, say Korea, right? So this is the list of countries, list of companies that are domiciled in US, while the ultimate parent company is actually in Korea. Okay, so now let's look at the log. So in the GPE log, the log.info log, it stores all the query execution logs. So now let's look at this. Okay, and here, these are the logs of our query execution. Okay, so here you can see that UDF finished iteration 1. Iteration 1 means it's the first select statement here. So if we go back to the query, and we can see that is this select statement, right? This is starting from the country and find all the companies. So that means in Korea, we have 194 companies in our database. right? And then we start from it, find its subsidiaries, and it took three other select statement to traverse all the subsidiary vertices, right? And the first one to find 44 companies, and among those, like 4 are already visited, and then selected 37, something like that, right? And then we can see the execution time of each select statement, and in the end, the query finished in 6 milliseconds. Okay, now let's try the other query. Another query will be like we want to start from US, right? Okay, now let's write another version of this called example 1 option 2. Okay, and now this time we want to start from US, right? So US, we don't need to take an input from it, so we can use this toVertex function to directly get a USA vertex. The type is a country. Okay, so now we have a vertex set variable containing the vertex US. Right now, I want to start from it. So these are the US companies, equals to select. Okay, so maybe let's save some time. Let's just copy this. So this is a query that we need to write to start from US. Okay, so it's very similar that we find all the companies in the US, and then we find we traverse all the way up to find the parent company, and along the way we want to pass the US companies in the set, right? So that we know, like when we find the ultimate company parent in C country, we want to put that US companies into the result in line 20, right? So line 3 is how I define it, and line 11 is how I initialize it with the US companies, and the line 20 is how I traverse all the way up to send the IDs of US company all the way up to the ultimate parent company. Okay, now let's run this. Okay, after running, I think we got the same result. And then let's look at the log again. Okay, so same thing, it traversed the 4 hops. But first hop, it traversed about 50K of US companies. Okay, and then starting from the 50K, you can see the number of edges being selected is way more than starting from the country Z, right? And you can see the overall query execution time is 241 millisecond. So it's almost like a 40 times slower than the other way around, right? So that we know choose the right starting point and the right direction to traverse really have very huge impact in the number of edges being traversed, and as well as the data structure being defined. Okay, so if we can make this decision rightly, if we can make this decision wisely, you can really the query performance can have a huge difference. Okay. And now let's go to example 2. So hopefully, let's do this really quick. Okay. So now this is a simple example. Okay. Again, given company A, find all the companies that are in the same country, and it is run by the same CEO. Just the example I gave, when I talk about the traversal plan, right? So again, where do we start from? Of course, we want to start from company A because that's the input, right? So what are the steps? So we have 2 options here. First, we find that the companies share the same set of employees, and then the companies in the same country, right? And then we take an intersection, we get the result. Or we traverse to a country and we mark it with the or accumulator or with a Boolean value, right? And then we traverse to the company shares the employee and see if they are in the country or not, so that we don't directly start from the country, right? And then these are the edges we're gonna use. And result, of course, we want a list of company. And in order to get result, we need the country and the employee, right? We need to make sure they share, they are in common. And what accumulator do we use? So for option 1, we don't need anything. We just want to do an intersection. And for option 2, we need a Boolean value to mark those countries, right? So we need to mark. So let's go back to the Graph Studio and run those queries. Okay. So for okay, so this is option 1, right? So we get the employees, and then we get the country, and then we get the companies share the same employees, and the companies that are in the same countries, and then we make an intersection and take the input company out from the set, and then print the result, right? So now let's see, let's pick a random one, like C15535. C15535. Okay, and that's the result. Okay, and now let's run another query. So this is the option 2. We start from the input company, and then we get to the employees. And when we traverse to a country, I only mark them to true, right? Because there is a local accumulator stored on the countries. I mark it to true. And then I traverse to the companies that are the same employees. And again, I traverse to the country, not from the country, starting from the companies that are the same employees. And I only make sure the country is marked to true, right? And then I print the result. Now the same thing. Okay, and now let's check the log again. Okay, so this is our last execution, took about 2.7 milliseconds. And we can also grab, say, UDF. So this is the line, the keyword in the line of the overall execution time, right? So you can see the option 1 took 43 milliseconds, while option 2 only took 2.7 milliseconds. The difference is like 20 times. But if you run this in a larger data, the difference can be even more, right? So yeah, so these are the examples. And okay, now let's check the questions.
So Xingyu, we have a few questions. One of them is, are these steps based on formal theory or just heuristics based on experience?
Right. So formal theory. So it's mostly a heuristic, right? Based on the experience. So because the GSQL query itself is like a Turing complete, right? There are infinite choices when you write a query. So sometimes there are a few rules that we can base upon and optimize the query. For example, like the less edges you traverse, the more efficient is the query, right? Or the more lightweighted data structure you use, the more efficient the query is, right? So we will also talk about like data structure in the coming episodes, and right. So the basic rule of thumb is like traverse less edges as possible, and also use lightweighted data structure if possible, right? And also, I see the question: do we have when will we have an automated query optimizer? Yes, I think eventually we will have it, right? Because we are developing our like a V2 query. So so this syntax V2 query, they are on top of query V1. So in the future, I believe we will once it's quite ready, we'll start to add optimizers to to automate this process. But as of now, the query with best performance is writing syntax v1 and follow these best practices. Yeah.
Cool. And one other question: how do we know our traversal plan is optimal? What are some of the signs we can tell?
Yeah. So we always have to debate with ourselves, right? See what are the possible choices, right? And then among the possible choices, you of course you can try it, right? You write the query and try it, and also you can just get more info, see from the logs, see if you have traversed the minimal edges or not, right? Yeah, so something like that.
Okay.
Yeah.
Great. Why don't we move forward and wrap up, because I know we're a wee bit over time.
Okay.
So should I share my screen?
Yes, please.
Okay. So that was excellent, Xingyu. It was great to see you. It was great to go into the logs and see how making changes to the traversal plan can bring orders of magnitude reductions or improvements to the amount of time it takes to run a query. Just to wrap things up, if you have more questions, we are increasing the places you can go to get those questions answered. You can join our developer forum. Please note we have a new URL for that, and we'll send out the slides in this presentation in a webinar. In an email shortly after this webinar ends, and so you can click on that URL. We're also providing the option for you to join our developer chat, which is on Discord. And last but not least, you can sign up for our developer office hours. That's every Thursday at 11 o'clock Pacific time. We have some additional resources. As always, we point people first and foremost towards TigerGraph Cloud. It's a very low friction, an easy way to begin to dip your toe into the water of using Graph, TigerGraph specifically. If you don't already have expertise, this is perhaps the best way for you to do so. To begin to develop expertise, it takes only a few minutes to open an account on TigerGraph Cloud, and it's free in perpetuity. And perhaps best of all, we have over 20 starter kits, pre-populated starter kits that you can use to help guide your initial learnings. And we also have our test drive online demos. Additionally, if you want to get more serious, you can download the developer edition of TigerGraph. And we also will provide any scripts on GitHub after the event's over. Our next webinar is on Wednesday, but this is being hosted by one of our friends, DZone. So the time will be a wee bit different. It's going to be at 10 o'clock Pacific. Please make a note of the time difference, 10 o'clock instead of the typical 11 o'clock slot. And if you want to sign up, that's the URL there, or you can go to DZone and register directly. So that brings us to the end of this webinar. We ran a bit over time. My apologies for that, but I think you'll agree with me. It was very informative. And thank you to you, Xingyu, for an excellent presentation. We know everybody in the audience had many other things that they could have been doing during this past hour, and we're very appreciative that you've chosen to spend the time with us. We hope you found it insightful, and we look forward to seeing you at a future webinar. Thank you.
Okay, thank you. Bye.